Welcome everyone, my name is Guanfu Cho. Today I'm going to show you how to systematically draw quadratic surfaces. At the outset, why are we going to learn this topic? This is essential when we want to address the triple integral or double integral whose domain is determined by quadratic surfaces. Thus, if we are adept at drawing these surfaces, it will be beneficial for solving problems of triple integrals or double integrals. Yes. Okay, so let's move on. First of all, what are quadratic surfaces? Considering the set of points that consists of the polynomial equations of degree 2 and 3 variables, it is a surface in R3 where the capital letters are real constant, just like this. Okay, we will call these surfaces quadratic surfaces. Okay. Next, I will introduce a novel perspective, that is, an integral's domain is determined by several quadratic surfaces. First, let me ask you a question. What is the volume of the solid bounded by this parabolic cylinder? Below by the plane, and on the sides by this circular cylinder. Okay. You may notice that the key to this problem is finding the domain of the integration, right? Then, how do we identify it? Okay, to solve this problem, let me first present the 9 categories of quadratic surfaces. If you want to check the structure of any quadratic surfaces, you can search 3D calculator GeoGebra, and it's a free website which can help you check those quadratic surfaces graphics. Here is an example. Here is an example. It is a special case in the first category, right? And anyway, let me back to our slide. Okay, so here are the 9 categories, and you can pause the video as needed to review each category. Okay. Okay, so based on the preliminary knowledge of quadratic surfaces, we can now proceed with a step-by-step guide for sketching quadratic surfaces. For instance, if we wanted to draw this hyperboloid of one sheet, x squared divided by a squared plus y squared divided by b squared minus c squared divided by c squared equals 1. The first step, fix one of the variables and construct a 2-dimensional plot based on the remaining 2 variables. Make sure to keep these 2 variables in mind, as they should make it easy to plot the graph. So here I choose x and y to be the variables while holding z fixed. Namely, z is a constant now, right? Okay, step 2. Reposition the fixed variable to the other side of the equation to determine its scope. Here we let z equals z sub 0, right? Then vary the equation like this. Okay, now the left hand side of this equation is non-negative due to each term squared. Okay, so 1 plus z sub 0 squared divided by c squared is greater than or equal to 0. Therefore, we can acquire the value of z sub 0 real and without any restriction. Okay, next, step 3. Let the chosen constant vary on its interval to sketch the equation's graphics, which correspond to the planes for observing the graphic changes. Be careful, planes are special cases of surfaces that are flat and extended indefinitely. Okay, the practical operations on this step are displayed below. Okay, so here, this is an example of varying z sub 0's value, choosing it equal to 0 in this time. Okay, then the graph of our equation is drawn by the red dotted line. Okay, you see, it's an ellipse. While the major axis of this ellipse might align with the x-axis or the y-axis. Here, I draw the major axis of this ellipse, aligned it with the y-axis. Okay, next. In the case of z sub 0 larger than 0, the current equation's graph is also drawn by the red dotted line. Okay. Last, in the case of z sub 0 less than 0, the current equation's graph is still drawn by the red dotted line. It's here. Okay. Okay, proceed to step 4. Choose one of the two variables to be 0 to draw the longitudinal or transverse section of the entire graph. Since we intend to draw a longitudinal or transverse section of the entire graph, we must select the right variable to achieve this objective, right? Okay, so here I select x to be 0, then we will receive this equation, right, whose graph is displayed below. Okay, so it's a hyperbola which is drawn in black. Okay, finally, the step 5. Optimize the final graph by filling gaps between each dotted line graph to make it 3D, like below, right? So here you go. It's the graph of this quadratic surface. Yes. Okay, now we can finally solve our initial problem. The value can be described by this triple integral, right? The only thing we have to do is determine the domain of this integral. So let's begin. And first, look at the equation. Z equals 1 minus y squared. See? But unfortunately, it misses one variable, right? That is x in this equation. So we must let the missing variable be the constant. Otherwise, we don't have enough variables to draw meaningful graphics in the following steps. So here we let x equal x sub 0. Since x sub 0 doesn't have any equation to be its restriction, right? Its interval is the entire real axis. Okay, so we have done step 1 and step 2 now. Let's proceed to step 3. Vary the value of x sub 0 to sketch several graphs of the equation using red dotted line, just like this. Okay, next execute step 4 and step 5. Choose y to be 0 to draw a longitudinal section of the entire graph and fill gaps between every red dotted line. Okay, so we're finished now, right? Next one, x squared plus y squared minus x equals 0. According to the same reason as the former case, let z equal z sub 0. Additionally, z sub 0 can be any real value. Based on this simplification, right, we can see this equation seems like a circle, right, in xy plane. Yeah. Follow step 3. We acquire the graph on the right hand side of this slide. Okay. According to step 4 and step 5, the entire graph of this equation is a cylinder extended indefinitely, right? Just like this. Okay. So that's 2 times x plus 3 times y plus z plus 10 equals 0. It's a plane just looking like this. Yeah, we have already know this one. Okay. Now we have done the graphs, right, which determine the integration's domain. Okay, so finally, the combination of these graphs is at the right. Okay, the purple contour is the region sought for, that is the domain. Okay, now we finally can start to calculate the value. The upper bound and the lower bound of z in this integral are 1 minus y squared and minus 10 minus 2x minus 3 times y, right? Here and here, okay, respectively. So the result of the integration of z is 11 minus y squared plus 2 times x plus 3 times y. Okay, just like this. Okay, now according to the graph on the xy plane, it's a circle, right? When we come across a circle, it will be easier for us if we adopt polar coordinates in the integrations. The key here is finding the upper bound and the lower bound of R, right? Based on my hint written in red, we can claim that the upper bound is R equals 1 times sine theta, and the lower bound is R equals 0, right? In addition, the upper bound of theta is pi divided by 2, and the lower bound is minus pi divided by 2, of course. Okay, and after a sequence of integrations, and we can acquire the result now. Yes. Okay, so to summarize, how do we draw quadratic surfaces? Follow the guide to select one variable being the constant, Then vary the constant value on its interval to draw several graphs with the equations. Next, choose one of the variables 0 to draw a longitudinal or transverse section of the entire graph. Eventually, fill gaps between lines to acquire the graph of a quadratic surface. Okay, thank you for watching.